Now that we have talked about regression by connecting it to the non-parametric models that we discussed first, like splines and regression trees, what we're going to do next is step back and make sure we have a clear understanding of exactly what regression is, and we'll spend some time understanding what can be done with it. So I want you to be thinking about comparing linear regression to a couple other models. And at this moment, I'm no longer talking about connecting it to the other non-parametric models, but actually I'm thinking of various parametric models that we might have. So we're fully in the parametric space now. Again, what we started with to introduce this topic was connecting linear regression to splines and regression trees, but now we are fully in the parametric side, thinking about linear regression. So suppose we have a data set like this. There's some variable x that could be equal to a bunch of different numbers. There are some numbers. And we have some variable y. Okay, suppose, I'll throw one more dot, that's my data set. Okay, and in this particular data set, suppose that x is just equal to one of these integers, 1 through 5. So there's lots of different models that we could propose and evaluate. One of them is called the equal means model. And that is exactly what it sounds like. The equal means model suggests that no matter what the value of x is, we always just have one prediction for y. In other words, if we use an equal means model, you don't have to tell me what x is in order for me to predict y. So if I write that down as an equation, I would write the equal means model says that the mean of y given x is just some number. Maybe I call it beta naught, but it's some number like 10 or 60. I'll write it in words as well. For any value of x, predict that the mean of y is equal to the observed overall mean. So if you observed in your data set that, so let's see, I didn't put any y-axis on this, 10, 20, 30, 40. Maybe you look at this and you observe that the average y value of all these data points is somewhere around 25, okay? Then I'm just going to draw a straight line there. That's the line for 25, right? So I'm suggesting that your prediction could be 25. If 25 is the overall mean of all the y values, just ignoring x completely, and then the equal means model would say, okay, whatever x is, I always just predict 25. And I can also do this with dots. So I could say, well, when x is 1, I predict 25. And when x is 2, I predict 25. When x is 3, I predict 25. When x is 4 or 5, I still just predict 25. That's the equal means model. That is not a good model for this particular data set, right? But it is one that we might want to use as a comparison. We might compare other models to this one. So equal means model. Another model that we might then think of is called the separate means model. That is also what it sounds like. If we have an x variable that divides the data up into groups, as we do here, so that x has to be an integer, 1, 2, 3, 4, or 5, so I've divided the data up into 5 groups. A separate means model predicts the mean for y that was observed in each group, ignoring all the other groups. Let's do it this way. In each group, where the groups are based on x, that word is supposed to be based. Okay, so let's see, let's try to do that. Well, if you look only at the x values, at the y values where x is equal to 1, where's the mean? I don't know, maybe right around here. If you look only at the y values where x is equal to 2, I think I just drew 2 of them, so the mean's right here. If you look only at the y values where x is equal to 3, the mean might be here. Only at the x values where y is equal to 4, I don't know, maybe I'll put it here. And the mean of y when x is equal to 5, I don't know. Let me draw another dot because I want it to be a little lower. Suppose that there's some dots there, right? Let me say it was here. Okay. I drew each of those dots without regard for any data that had a different x, right? So the separate means model says, if you have a new observation in the data set and you tell me x is equal to 3, great, I'm going to predict the average y value that I saw in my data when x is equal to 3, completely ignoring all the other data points that have different values of x. So in some ways, that's kind of the opposite of the equal means model. Right? The equal means model says, hey, just combine all the information without regard for x, and your prediction should be the mean of y that you observe. Separate means model says, look only at the data points that have exactly the same x as your new data point and predict the mean of y you saw. So I want you to think of linear regression as one possibly useful compromise between these two. A linear regression model says, well, let's see if it makes sense to write down this equation that the mean of y given x is some intercept plus some slope times x, okay? So if I try to do that here, I'm going to try to draw a line that is as close as possible to the means, okay? Now, was I able to draw a line that went exactly through every red dot? Nope, okay? But I drew a flat line, and so if I want to know, if I estimate the intercept and slope of this equation, which we'll talk about how to do that at length, what I'm saying is that if you tell me your value of x, my prediction for y is going to be a point on this line. So I want you to see, let's put in green so you can see how these three models differ from each other, right? For each of these three different models, if you tell me x, I'm going to give you back my prediction for y. But they make different assumptions. The equal means model assumes that the x variable doesn't matter at all. The separate means model assumes that x matters so much that you should actually throw away all the information from other data points that have different x's when predicting y. The linear regression model says, hey, you know what? Maybe it looks like the mean of y given x follows a line. And if so, let's make use of all the information in the data to draw that line and then use the line to make your prediction. Next, I want to explicitly write down the assumptions underlying a linear regression. And they should sound a lot like the assumptions underlying a pooled t-test, except for the first one. Okay. So the first assumption underlying a linear regression is called linearity, although that's kind of a misnomer. The linearity assumption says that the equation you write down to relate the mean of y to the predictors has to be correct, right? Any conclusions you're going to draw based on regression, make the assumption that you have the correct model. So again, linearity is the assumption that the equation relating the mean of y to the predictors is correct. Okay. So this assumption is crucial in that if it's not true, then nothing else you're going to use the model for is going to make sense. But it's not only crucial, it's also usually not true. Why would real life follow straight lines or follow an equation that I can write down? Maybe if you're doing a physics experiment, maybe it's true then. But in almost no other case, certainly not in social science, certainly not if you're dealing with people or if you're dealing with animals or plants. Things that are alive don't follow straight lines. So here is a question for you. Suppose I have data that looks like this. Here's x, here's y, and the data looks like this. Okay. And suppose that I notice that it's a curved pattern. That's not a line. And suppose that I choose to write down this equation, the mean of y given x equals beta 0 plus beta 1x plus beta 2x squared, okay? And so what this says is the mean of y given x should be modeled with this parabola. That's the equation for a parabola. My question for you is, does the linearity assumption hold if this is my model for the mean?